Okay. So what is supervised algorithm? It is what is support vector machine? It is supervised algorithm. Supervised learning methods. Okay. Used for classification, gradation, and right. Outlier detection is useful in identifying, which is, some fake things, fake transactions. These are useful in outlier detection. That means you have some data, you want to find which is fit not as per the trend of the data. So it is very useful in identifying security threats, identifying fake transactions, right? Outlier detection. So this is where it is. So the advantages of SVM are effective in high dimensional spaces. Number of, this is very important one. Number of dimension is more than number of samples. Got it, right? Number of features is more than number of samples actually. In those data, this comes very handy. Useful. Use subset of training points in. Okay, so this is what it uses subset of training points rather than using all the data. It uses subset of information, and this is what this whatever subset information it is using, right? It is known as support vectors. Whatever minimal information it is using, support vectors in detection, in decision function. So we versatile. Different the core logic function, right? It can be, externally it will be different. The way it does the finds, the way it separates the data, the way it does the algorithm on the data can be changed by changing some logic. Like in various function, we give some argument function name, right? So using that we can change it. So you have various types of SVM because internally it can use your different type of kernel functions. Kernel function is what? Kernel function is core algorithm which can be changed. It will be support vector machine, but core algorithm will be changed. Okay, it's never fair to talk only of advantages. Let's talk about disadvantages as well. if remember this point, huh? If number of features is greater than number of samples, avoid. Okay, so understood, right? If the number of features columns is more than the number of rows. Okay, remember in UCI we saw some data which has 40,000 columns. If you click here. No, no, no. No, no, no. Ah, right. So that is what usually. So if you see here, number of attributes, you'll see some attributes will have thousands of. This is something. No, that was also. There is something we will get. Hmm? This is one. But more so in we'll get some 10,000, 20,000 columns. Generally, actually comments, right? Comments words. Okay, so there it becomes. Uh, see, this is the type of data. Understood, right? This is the type of data. This is the so what are the huh? Huh? Yeah, what does it mean? Okay, so what does it mean basically? If the number of features is greater than so number of features is more, that means number of variables will be more, right? If number of variables are more, what will happen? Whatever formula it will generate, it will take too many of those variables, right? Right? It will take too many of those variables. If it is taking too many of those variables, what will happen? The function will be more complex, right? So when you are generating complex function, what are you getting out of it? You are getting out of it more less generic functions, right? You remember if you increase the degree of polynomial, right? If you keep increasing the degree of polynomial, you will generate a complex function. If you are generating a complex function, what will happen is you are creating a placeholder for a lot of variables. Not right, you're creating a placeholder for a lot of variables. If your lot of variables are there, you're making more specific function, not a generalized function. Understood, right? So always number of columns, number of variables, number of columns should be minimized that way. So there will be a generalized function. Generalized function means that has less overfitting. It works in more cases. Okay, that is what overfitting about overfitting and using regularization. Regularization function means whenever you have coefficients, right, it is spiking up. Regularization function reduce the spikes. Okay, so that is your regularization. Regularization functions. Okay, so these are randomized. So if it is too much of columns that you're getting, so you have to make sure you're using the right kernel, right core logic method. Okay, as well as you are taking care of over creating those variables. Hmm? Yeah, so you might have to do k best first. Select k best, right? Okay, so you can do that first. Okay, it does not provide probability estimates. Okay, let's now see for classification what all algorithm to use. SVM for classification. First, okay, one is SVC. SVC is support vector classification. Then one is neo SVC. Okay, so SVC and new SVC and linear. So what are these two methods? Yeah, first let me explain SVC. So SVC is it is based on just a few things here. Okay, so it is okay, it is based on a mechanism, a library based on just know this SVM. Okay, and the important point here is its fit time complexity is quadratic. What does it mean? The training takes a lot of time, more time. So if the data set is, I mean, in the training time is, exponential. It's not exponential. Quadratic to data, fit data. Quadratic to sample size. Understood, right? That means for if the sample size is way more than 10,000 samples, it takes a lot of time. So this is good for smaller data sets. If sample size is more than 1,000, that's good for takes a lot of time.
This will not recommended.
No, for smaller data set, this is fine.
Greater than 10%.
It's not recommended. Okay. So how is it? See, all this algorithm was how they do classification is they are basically by classification algorithm. What they do, they divide the data into two parts. Like you have to divide entire data into job profile, like salaried employee, salaried, self earning, unemployed. Like 4 5 categories are there. It will do first do salaried, non-salaried. Then it will take non-salaried data, self-employed, non-self-employed. Okay, it will. That's how it does multi-class classification. Understood, right? All right. First time it will keep it separate. Whatever data is there, it will take it separate. Again, split it out, make it separate. That is how it does.
Is it like binary tree? Binary tree.
No, no, don't take it tree. I mean, how it will do classification, right? All these algorithms are by default one-to-one class. Okay, so because of it, it first try to break the data. Rest of the stuff it gets, it again tries to break the data.
So how it will break the data based on condition or
First, it will no. The how it starts with initially, it will understand the logic. Uh, I mean, it uses some kernel technique, some logic, okay, which I'll be explaining in a while, to break the data. Okay, but it will split the data in only two parts, not 5 or 4 parts, depending on number of classes. One part will be class one, non-class one. Class one you separated, you take that out. Non-class one you get, then you break the data class two, non-class two. Class two you got. That is how it does actually. Okay, most of the algorithm are by classification, and how they implement multi-class is using this tactic. Right, how suppose a lot of data, a lot of information is a lot of there's what do you call that, uh, a lot of alphabet games like Scrabble, Scramble. Scramble, right? So you have that. Suppose you have to separate all this. First you'll do, okay, let me bring A first and then rest of the stuff, B first, rest of the stuff. This is how it works, and rather most of the algorithms, this is how it works. Okay, so this next is a new support classification, where support vector classification. Similar to SVC, but uses a parameter to control the number of, like in earlier case, number of, see here, in all this algorithm, right? So it uses some support, I mean, it's limited data to control the logic that is generated here. Okay. And you, SVC, here you pass some number, right? you pass some number which controls number of support. So what is support vector? Support vectors are subset of the entire data set which is used in creating the logic, right? So with when you, in NU SVC you pass NU, which is like number of support vectors that you want it to control, right? Number of support
Means splitting of the data.
uh, hmm?
How many number of splits you want?
No. So in support, see, the support vector machine. What does it do? It actually you get some subset of total data and creates a logic. To put it simple, right? Earlier in logistic regression, we created a line using all the data. Here, it will choose some subset of data, create a logic separator for that. Okay, in a simple words. Now, how many points do you want it to use to create a separator? That is controlled by any.
Like entry points to decide the line by classifying.
Got it, right?
Mm-hmm.
Okay. Okay, and the third one is linear SVC. Okay, so this is the most flexible one among all these three. Okay, most flexible one. Okay, supports both dense. Okay, so we'll see this. So this is, remember, this is like more flexible. It has more options. So if you have basic smaller data to take care with, like less than 10,000 rows and more columns, this is first one is fine. But if it goes beyond the certain linear, this is good thing. Linear, this is what it is based on some other mathematical library. It tries to predict it tries to predict in a line or a curve for you, and it is more flexible. So we'll see the usage of it. Okay, just some basic definitions. Okay, so remember, all these are capable of doing multi-class classification. Okay, so let's do a thing. Let's use our this guy. Okay, so we'll learn how to use them. Okay, first let me show a small example using this. So let me. I'm just trying to think the data which would show present. Okay, so let me take a small case. Okay, from sklearn import SVM.
So how do we decide that when to use SVM based on the data?
Which one?
How do we decide that we need to use SVM?
SVM is generally good for non-linearly separable data. That means data is too messed up. Okay, data is too jumbled up. Okay, see, in logistic regression, what do? You basically try to create a separator. Decision tree tries to ask a good question and separate it out. When the data is little more jumbled, okay, little more inside one data, there is another data, and if you want a separator, this type of data algorithm is good. Okay, and
What's the best any best example?
any best example is suppose you have two points. Okay, the points one. Okay, let me show it right now. Let me rather generate some data like that, which will actually.
clustering options on mobile.
Yeah. Okay. Okay. So let me show. Suppose you have some data, okay, where all the data are there, and middle of it, this other data separator. Suppose two type of data are there. Let me draw a diagram. Okay. Suppose you have this data. Okay. Suppose this is one data, and suppose this is one data. Understood, right? Suppose you have, and you have to do a classification for this case, separating one from other. Okay, how will you do that?
By using kernels,
Huh?
by using kernel only it is possible.
Yeah. So what you do is you can increase
non-linear to linear, and then we can classify.
exactly. So how this thing happens over here is you add one dimension to that. Your algorithm, it will increase the dimension of your data. Okay, it will bring all the blue data, right? It will add one dimension to the blue data. So suppose all of the data is here in one plane. You add dimension to the one type of data, it will come up. Then you can create a plane which separates this, right? So this type of data, when it is available to you and you don't think the linear logistic regression or those things would work, then this is the thing that you do here. Understood, right? Hmm? PCA, it's little different. There, you're trying to reduce the number of dimensions, right? I mean, it of course needs changing dimension, adding dimension, and all that. But essentially, trying to do is you're trying to reduce the dimension. Okay, maybe you from the existing data you are converting into in some other dimension so that your actual dimension is reduced. Here, the blue one you will pick up, increase the dimension. Okay, then what will happen? There you can create a predict a plane, right, which will separate this data. That's all it is. Okay, so essentially what it is doing. No. Okay. So now, okay, let's now see some examples. Okay, it will be a little confusing from now. Just a second. Let me get hold of some good examples.
Algorithm itself will identify some data.
Right.
To
To
add.
which data to add dimension. Right. That is why it is very computation intensive. Okay. Understood, right? The way the core fundamental logic, how does it work? Okay, so let me show some, uh, that some dirty example which can make it clear. Just try not to. Hmm. Okay, so we understand one thing: linear. What is linear separation? You're creating a line which is separating the data. So I think everybody understands how is that possible. It will try to predict a line, and it just let me show one diagram. Okay, how does that work? Linear separation. Okay, this is the data, of course. So nothing but creating a by class data. Okay, so y is there, right? This is x, this is y. Okay, by classification. So now this is the model. Okay, what you did here, you just train the model, and what is the kernel here? Linear color. That means you're trying to predict a straight line here, linear separator. Okay, and okay, and you have this option here. Actually, if you don't give, okay, just keep this and leave some default. So what will it do? It will try to predict a straight line for you in the entire data. Now, okay. So from the entire data, what will it do? It will try to predict lines, okay, which is separating this data. It's very simple, right? What will it do? I'll just, whatever line this guy is predicting, right? I'll just plot that, okay, and it will be clear to understand what is happening over here. Okay, and what is the model name? Model name is model, right? If I do model dot, you'll see something like vectors or something is there. Support vectors. If you do this, right, these are the 3 points which are support vectors. What are these points? These are the points which is actually making the line actually. Okay, so let me just show these points. So these are support vectors, right? So I want to show them separately. Support vectors. Okay, so what this algorithm did, let's understand this. This part is clear, right? SVC kernel linear. Kernel linear means you're trying to predict a straight line which separates the data. Okay. Okay, fine, right?
If it doesn't give the kernel,
It will by default, I think it takes linear only. And then I think it tells you. You can see what does it take. Default RBF, sorry. Okay, so you have all these options: linear, poly, RBF, sigmoid. DN means straight line, poly means polynomial degree. RBF is RBF, some scientist name it gets right. Some scientist name it gets from. Right. Then you have sigmoid. Okay, RBF is generally works for all of them. That is why I give it. So in this case, what you're trying to predict, you're trying to predict a straight line. That is why you give linear here. Okay. Okay, and then you have sigmoid. What is sigmoid? S curve. Remember that sigmoid. Sigmoid. Huh? This curve, S curve. Huh? Activation function, yes. I mean, we'll anyway in deep learning, I mean in TensorFlow, we'll learn more of sigmoid. But in logistic regression, what is that you predicted? You predicted what is the probability of output that is getting generated in 0 or 1, right? So use this sigmoid curve here. So it has a probability to generate all of these options. Okay, you don't have to do anything, it will generate all of this. Okay, so now
Sigma is 0, 1, then what is this linear, linear, rectified linear unit?
Relu. Oh, she's studying. I mean, she's bunking classes here and
That is
studying.
also 0 to 1, right?
Huh? That is
Is there
actually.
anything less than 0? My negative is 0, positive is 1, and linear is rectified linear unit.
So there
How
is
is
like
it different from sigma?
no, there is a lot of. I mean, this is a simple question, but there is a lot of. Relu is in neural networks. Relu works better.
How sigma is different?
Sigmoid is nothing but it will actually try to predict from your data, right? It will try to predict the S curve.
Yeah, here also it's saying 0, 1.
Right, it is 0, 1. Okay, so what it is doing, it will try to whatever data, sigmoid is generally a function actually. Whatever data you give, it will translate into 0, 1.
So negative is 0, positive is 1. And rectify linearly.
So it's deviating. So what you can do here? So in rectified linearity, ReLU, right? You can control the upper limit there. ReLU 6. That means whatever data you give above 6, it will convert that to 6. Okay, that is ReLU. So all these are your functions which simplifies your complex task. These are smaller elements of a complex function. So it will be very difficult to explain that from directly like this. Okay, once we get into the Christian function and understand those things, then we'll be able to follow. It will be very difficult to answer jumping here directly. Okay, so if you want, you can check out this place. So here itself, I think Relu, and so yeah. So here itself, see, it is trying to compare sigmoid and have a look. Yeah, this is your sigmoid function. Okay, this is a so what is if the number is this is the value. If the number is less than 0, it will make it 0. If the number is more than x, it will make it x. In middle, it will be like this. Understood, right? Okay. This is sigmoid. Whatever data you give, it will make it between 0 and 1. This is ReLU. Whatever data you give, it will make it. If it is 0, if the data is less than 0, then it will be 0. If it is more than 0, whatever is the data will be here. Understood, right? That is your ReLU function. And there are a lot of
It's not between 0 and 1.
No, rectifier is not.
Only sigmoid is between 0 and 1.
Okay, so if you see SV is these points. Now what you want to do, you want to plot the SV also in the same graph. SV, right? PLT dot scatter SV colon comma 0 SV plot K. See, these are the 3 points. See, it is on top of here. See, this guy is on top of red, right? Did you notice this? Huh? Uh, wait. Size of point, size, right? Say 100. Now it is clear. Huh? Or maybe we should go. So, okay. So these are what is this algorithm doing? This is choosing these 3 points. Okay, not the entire data. You see, it is saying, okay, these are the end points of this data. This is the end point of this data. Now it will use these 3 points to create a separator here. Understood? It will use these 3 points. So what this algorithm did, SVM fit algorithm did, it basically returned you these points, isn't it? Now whatever line is there, it will draw inside. It will try to draw inside it. It will try to predict the line. And remember, what is the difference here? Whenever there is a line here, separator, okay, there is a cushioning factor here as well. There is some gap. If there is a lot of possibility that you can draw a line here also, you can draw a line here also. There is some space here which is yet to take a call. So that is what this guy does actually. Okay. Okay. So what it does, it tries to predict the line for you. Okay, now suppose you have little more complex data. Right, understood, right? What is supposed to happen? It is supposed to predict a line based on finding some important point. That is how what is the heart of correlative machine.
So internal array one dimension.
So this in that case it was simple. No need to add dimension. In this case, dimension is required or not required? Huh? Right? Two planes, right? How do you separate two planes? So dimension is required here.
In that case, it doesn't apply any dimension.
No, not required, right? It will simply add a plane. I mean, without dimension, it is creating a plane. In this case, you need a dimension here.
But it shows 3 points, right? So which one you need to decide?
No. These 3 points will be used in predicting the separator, in finding the separator. So you found out 3 points. Okay.
You got the 3 points. So how to find the separator?
This is what algorithm does. Now from these 3 points, it creates a soft boundary. From these 3 points, it creates a soft one. Suppose the next point that you want to predict is somewhere here. Okay, next point you're trying to predict it here. So based on the boundary, okay, based on the boundary that is predicting this point will be identified in this class red.
So based on this output, we'll apply another algorithm to predict.
Now same algorithm, like if you want to predict, right? So your model is created, right, above. So we'll do model.predict. Understood, right? If you do model.predict, pass some points. Say in the above case, what is the point you want to pass? You would pass this 3 and 1.5. Sorry, 1.5 and 3. Class 0, right? 1 point. Let's go little down.
So there's only 2 classes, right?
Classes, 22 classes. So the here this right here it is if it is 2 and 1, if it is just saying if it is 2 and 1, and it is predicting the class below. So what it is trying to do here. I mean, in the above case, it is trying to find the points. Using that, it will create a separator if required.
I didn't understand this.
This is a graph that is data that is generated. In middle of the data. So can you draw a line in this curve or draw a plane? Can you do that? You cannot do that, right? Without increasing dimension, you cannot create a separator. So what will you do? We'll now actually create a if we apply, right? So let's apply in this data, right? This is x and y, right? In this data, let's apply the points. Okay, this is your x data. Okay, and the y. This is your y data. Okay, let's use our algorithm here. Okay, what we'll try to do, here it okay, so we have this data. So CLF is the algorithm, right?
Yes.
Okay, so do CLF and sorry, first let me see one data. See and see, so here minus 5 and minus 1. What is the data? 5 and minus 2. 5 and minus 2. Oh, sorry, it is 5 raised to the power 10 raised to the power minus 2, right? So it is what? 0.05. 0.05, right? This is 0.05 and it is actually, let's generate some data. That's very difficult to make circle. So that's okay. So it is, what is the data? 0.5. This is 0.5 and this is point, that is, this is This is minus 0.05, right? Let's take this point now. Oh, this is too small. Wait, let's just change the data. Okay, can we give range here? Okay. Okay, so let's do this. X into x is equal to 10 into x. Fine, right? See, now the data became in the range of minus 10 to plus 10. And if you see x, right, it is much more calculatable, right? So you have this first data is minus 1.4 and this is, sorry, 1.4 and this is 1.6, right? 1.4 and 1.6. This is class 0. So data which is 10 and 0 sort of data, right? 10 and 0. 9 and 4. 9 and 4 is that. Okay, so let's do it. So what we'll do, okay, so now what we have done, we have created a model CLF. Now we'll pass on it and see which class does it belong. It is able to predict or not. Okay, CLF dot predict. Okay, and what is the data that will pass here? Let's do one of them. Minus 1 and minus 1. What is minus 1 and minus 1? Minus 1, minus 1. It is predicting class 1, right? See, this is the data, minus 1, minus 1, this is class 1. And then 10 and 10 and 10. What will it be 10 and 10? CLF predict. So this is minus, so it is identifying that in this way. 10 and 0. Say that.
Pass only 10 and 10. It will give that. Minus 1 and 1 you remove and pass only
Minus 10 and
0.
So whatever plane it is acting. Now see. Okay, so what is it doing? Minus 10 and 0. This is this guy, right? So even if the data is this complex, one in Z, it is able to do that using this algorithm here. Okay, if you want to know the support vector points, CLF dot support vectors. Right. See, in this case, earlier, what was in case of straight line, what was the support vectors? Very less, right? In this case, you see that is because the number of planes have increased now. And how many support vectors? In this case, you are not considering the support vector, right? Okay, if you use NU SUV SVC, you will be controlling the number of support vectors you are using. Okay, that will prevent it from. This is what support vectors will tell you actually. Okay, so here CLF. If you do this right, you'll find all the options. So here dual codec. Like if you want to see the kernel, linear kernel, it is added. That is because we have
Linear means by default it is a quadratic.
Straight line. So for quadratic, it is POL.
The polynomial type it is
POL, yeah.
In this case, the straight line means it can't be. How can it be possible to?
See the error. This is the score error, right? This is error is around 60. I mean, the score is around 68%. Yeah, you saying something?
No, this is a linear. It's applied the linear, right?
Right.
So it's the straight line. How it
Above data and this is straight line. I mean, straight line plane actually.
we can see the dimensions there. Support vectors.
Support vectors, yeah. We found out all the points that is deciding what is happening. So what we can do, we can print all these points, right, as we did earlier.
And how we'll know which dimension it's applied?
Just a second.
Where can we see that?
So SV colon 0 SV colon 1 K 0. Okay. So these are the support vectors that it chose. In creating the logic. Okay, so since earlier data was simple, only 3 points were sufficient for it. Now data is complex, right? Data is complex, so it use this many data here.
Vectors and
Support vectors. I mean, they are the one. Actually, here I will plot you the whatever. Right, this is what I have to do. Same data, right? You guys wanted to see how does the content look like, right? We have to plot a 3D plot actually. Let me see if this will work. I used it in the past for the same data. No, sorry, the function that is it. These are inbuilt function interact. Okay. With this 3D is coming, R is not defined. That's R.
Z level.
Huh?
Z level. X, Y, Z. Z level. R is not defined.
Are you seeing it? Where is this line? This line.
Thus, there is not scatter. No, scatter 3D X.
R function. Acha, right. Right. R is nothing but it's generating some values. It should show dimension. It's a wait. It is taking this some values as 0 in this case. X, whatever is value of x into 2. Acha, maybe I have multiplied it 10 above, right? Okay, because it is trying to come. Oh, SV was recalculated. Right? Model training and everything is done. Now let's see. Sorry. Is there any way? Huh? You understood? This is 3D graph actually. Ideally, it should print, this guy. Okay, just let me try one more time. R is equal to. No, this one. So essentially, can you see the 3D thing here? I mean, it actually adds only one dimension more. Okay, what it does, it brings that the fluorescent points above. Okay, even if it works out, it should print you. Let me show over this the earlier. Okay, let me try once again. Something like this, it will show. Something like this. Understood, right? How the points are separated. So this is how it separates this plane, and the plane will be whatever line you are predicting, right? It will come here, and the lighter points are the one which is used for doing the prediction.
But the support vectors has so many factors.
So all those points are, see, support vector means those points are considered to create a plane, create a logic. That's what they means. They are used among all the points. Okay, they are the one who are the chosen one who will be decided. I mean, when you have a lot of data set, right? You don't need a lot of data set to create the logic. Okay. So what is support vector doing here? That those are the points which are creating the logic for you.
It will choose all those black dots.
All those black dots, right?
Based on that thing, it will
generate a plane. Yeah. In this case, it will generate. See, among all the data, do you think this data is required? This data, if you have these two data, this data is required compared to this data? No, right? Okay, so it will not use this data. This data is required compared to this data. It will not use this data. So it will use typically this data which is nearby here, data which is nearby here, and it will be used in finding the plane for it. Fine, right? Huh?
This could be
What? That's fine.
In yellow, there's no light color.
Hmm?
You choose. Here in red, you said whatever is the light color, that those are the supporting.
I mean, light color. This is a light, huh?
You said that light. Whatever is light.
I mean, I thought these are light, and I mean the points which are deciding factor actually.
Yeah, but
Okay.
in yellow, it's not. Nothing is there.
Yeah, because all of them are light. I mean, same color, right? Yellow, light.
No, I'm serious. Which points have to choose from?
So
See,
here,
these are the light points.
right, here it will choose the points which are closer to this. Understood, right? So you see, if you have to just forget about SVM and all that, if you own the entire data, if you think some data should be important to decide everything, it will be this data and it will be this data, isn't it? Others are non-important here. So what support vector machine does, it finds those data and uses those data in predicting the plane for you. Okay. just if you have to understand SVM in the simplest understand, it will add dimension whatever it does. There are two things that it does. One, it finds important points. Okay, if you see mathematically, a lot of things happens inside it. Okay, without going there, you just put it across into two things. One is it finds important points, that is known as support vectors. Then using that, what it will do, it will try to increase the the planes, that what type of separator you want to find out, right? It will do that. If it is doing all that, then the third result will be a plane which will, or plane, or what sigmoid, right? Sigmoid plane, right? Whatever is it, it will try to calculate it out. That's it.
So if I give some value, so it will try to predict the with that support vector thing basically. If I give some 5 comma 10, so the 5 comma 10 is lying on what support vector it is predict, which is the nearest support vector it will predict.
Right. And that will decide which class does it belong to. Okay, this is only in terms of classification. You can use support vector machine for doing regression also. Say in this case, if you have outliers, how do you predict outliers? What it will do, how it will do for you, how does it identifying outliers? So it will try to fit every data. It will try to increase the number of dimension, right? If it is increasing the number of dimension, for to fit some data, it will have to add more and more dimension, right? Those are the data that will be outliers. Okay, this see, suppose there is no outlier here. Suppose there is one point which cannot be separated using these two planes. Understood, right? How will you identify outliers? In this, for most of the data, adding one plane is sufficient enough to separate the stuff, right? So, okay. So now suppose, okay, uh, okay, having one more dimension is enough to support this. First thing, if there are some data for which this much dimension, adding one dimension is not sufficient. Understood, right? If there is some data for which adding one dimension is not sufficient, then you will say that is an outlier.
Basically more than one dimension.
No, I mean, sorry, I don't quote me as one dimension. So for most of the data, adding two dimension is sufficient to separate them out. If you have to still, I mean, there are some data which is still not separable, you will say these are possible outliers. Understood? See, for how adding dimension and creating separable works for some lot of data, not for few data, that means you'll say these are extremes, these are outliers. That's the key logic. Okay, let's see what are the various options here. Okay, so now we have seen this case, right? Now I'll just show you one more case. Okay, you have it is very highly configurable. I'm just not showing these details now. Okay, suppose you have this data. This is RBF kernel. Okay, now if you do clf.scope x, what do you get now? Got it, right? Okay, so what happens here? Earlier case, this is the data which gets separable. What is the accuracy that you are getting earlier using kernel method? 68. Now using RBF method, you are getting 100% accuracy. Of course, this is training data. We didn't divide the data into training test data, but what it is doing, it is actually, so now you want to see the, so earlier we saw the points, right? Now if you see CLF dot, what is that called? So it is now completely able to separate data creatively using this RBF technique. So support. See, you'll have lesser support vectors, isn't it now? If I try to point it, see, it is using far lesser points to create a plane here. Understood, right? So RBF linear is something which will predict a straight line. RBF, it is able to predict adding one more, in the earlier case, adding one more dimension predicting a straight line. Here adding one more dimension and predicting much more convoluted. Like you have 2-3 layers of data. Imagine spiral data, outer one layer, middle one layer, middle one layer. Using SBF, using SVM, you will be able to do this classification as well. Understood, right? Okay, SVM is good, has worked very well with image classifications. Okay, let me show one. I think sometime back I was trying to show some images. Okay, let's see.
Image.
PCA and SVM together works very well for image classification. It is downloading this stuff.
So which features of image SVM highlights and which features of image?
Huh?
Which features
So
of
feature
image?
selection will PC will do. Remember we predicted the T in the phase. T was important, right? Feature selection. Then after doing that, you'll use SVM to do the classification, because SVM can understand non-linear data. Just keep in mind, guys. You can see that this type of convoluted data. If you apply linear regression on this data, we can see the accuracy also. Logistic regression. We have this data, right? Let's apply logistic regression. See from sklearn dot. Oh, it is still downloading. No. Oh, these are around 200 MB. This is around 1348 images, should be. Okay. Each image is of 62 cross 48. Okay, so we'll now do a problem using SVC and randomized PCA. Okay, using make a pipeline, we'll try to identify phases. That's the project, small project. It will clear how to use it and all that. Huh?
With this, what will achieve this?
So with SVC you can do non-data, you can do classification or regression using, this is one more algorithm. Okay, so in earlier case, as we tried for classification, we tried various algorithm. You can add SVC also to that list. And if the data is non-linear in nature, this guy would work very well.
Generally, the more data what you pass for training, that gives more result, right? I mean the exact result, right? But here we are reducing that. I mean the points, in the sense that reducing the data itself. I mean the picking the data is reducing.
Right.
So
Sorry.
no, generally, the more trained data which we pass for the algorithm, the more accuracy it will get. Will get it right while predicting it. But in this case, we are taking, I mean, the less data to separate and to train it and all. So how different from that to this?
So here basically it is good at identifying what the important data. Okay, less data is not the key. It can run using important data.
Okay, so the algorithm itself, it will pick you the what important data.
If you remember when we saw one diagram, there I showed you that path, right? How is the entire path? That SVC comes very handy when the data is less. See, in case of classification, if it is less than 10,000 data, what is the thing you have to do? Linear SVC. Understood, right? So it is very much in line with this. Okay. Okay, so it has downloaded everything. Okay. So let me finish this, do this project now. We'll identify faces. Okay. But first we want to see all the content of the faces, right? At least some of them at least. What are these faces? What are the persons? Okay, so total how many people are there? So 1, 2, 3, 4, 5, 6, 7, 8. Right? So these are the people. Okay, these are different people who are present here. Who are these people?
Yes, sir.
Yeah.
Bush.
Hello?
George W. Bush.
After
Tony Blair. These two.
Achha, give 10 minutes, then I will just stop. So here, okay. So first thing that we need to do, I mean, how many features does it have? Total number of features per image is 60. So total 3000 pixels per image, right? How much? 6247, right? What is 6247? See this? 6247 is around 3000, right? So we have minimum 3000 features each image. We don't want to work with so much of features. It will take a lot of time to compute. We'll use 150 features only. So what will you do? We'll use PCA to find 150 important pixels from each image. That is what PCA will do. Okay? 150 important pixels. Okay, we'll use randomized PCA, which works for mostly for random data, and it has a good random behavior.
I think new Apple X. They are using this chips in face detection.
SVC.
I don't know which algorithm it is,
Oh.
but
It is a deep learning actually.
they are using this.
Nice. So what you have, this is a PCA that we did here, right? So what will it do? It will try to, among 3000 features, it will find out 150 features only, 150 pixels, right? Identify 150 pixels. Okay. Now so all this RBF is good. Okay. So okay, class weight balanced. Okay. That means your data is not unbalanced. Right? Data is not unbalanced, so class weight will keep balanced. Okay. Then what you want to do? You want to create a pipeline. First it will do PCA, then it will do SVC, right? To data in the pipeline. Okay, we'll identify that. Given a photo, it will be able to identify who is that person. Right? If you give your photo and your family photo, if you train it properly, it will be able to do that. Okay, provided you keep it compressed. Okay, you created the pipeline. After this, what will you do? You'll divide the data into train test data and all that, right? The entire image data into train test. So that we can find accuracy. So what is it? Faces data, faces target. Target is the name of the secretary, right? Okay, you created train test.
What is the random shape? What is the default thing?
I mean random number, just to randomize which data to use for training test. If you use 42 number, it will again divide the data into same parts. Model selection, sorry, not validation, selection. Okay, so and now, right, you remember grid search. So what will you do? We'll use grid search on it to find the best parameters. Okay, because as we remember, SVC takes lot of parameters. So whenever you're doing SVC, you have to use grid search techniques to find which are the best parameters. Understood, right? Okay.
To find hyperparameter.
Exactly, because it takes a lot of parameters. So now,
When the feature selection and hyper both are same, is it?
yeah,
What is
feature selection.
hyperparameter?
No. Feature selection is selecting important columns.
Features.
So hyperparameter is the model initial parameters you have to select. Model initial parameter, like in SVC, like in this case, right? SVC, you have this many options, right? This is one parameter C, gamma. I mean, I'm just showing you there. It takes a lot of options. SVM, right? So this is this two parameter, and you're creating a grid here. So okay, grid search is done. Okay, so now you want to see the best parameters so that you can configure the pipeline with it. So you do like this, best parameters. So here only you should you'll find all the options here which is used to train. Okay, so what happened? It didn't execute it here. Grid. Do you see estimator? Best estimator. Okay. Oh, sorry, I forgot fitting it, right? Okay, it might take some time. It might take some serious time. Okay, so what it is doing, it is training the model. Randomized, what is it doing? Randomized feature. Yeah, it is done now, right? Okay, so now if you do grid dot, it will have some best estimator, best params, right? It will show you the best parameter for this class. Then grid best estimator. It will show you the best model which was selected here, right? After this, what you have to do? This is the model we will use for prediction, right? Model. So you created a pipeline. You added into grid search to that to find the best parameters. After finding the best parameter, you want to do the prediction. Okay, you wanted to do the prediction. After doing the prediction, if it is a prediction, right? Now you want to test it. Okay, so remember faces. Faces look different, right? Somebody might see in this way, right? Faces are different data. Let's see how accurately you can correct. So remember here. So okay, so it corrected all of them actually correctly.
No, the bush is wrong, the first one.
Why is this? Oh, this is Bush. There are two Bush, right? One is Bush 1, Bush 2.
No.
George Bush, father, you know him?
No.
Huh? He was also president, right? There are two Bushes. Senior Bush, yeah. He's senior Bush. This guy.
But it looks like Trump there like this. It looks like...
This is Bush, right?
No, this is Bush, correct.
This is Blair, right? Yeah. This is bush, right? Right. This is correct. This is correct. This is correct. This is correct. This one actually, I think, this really looks like that. This is bush actually. This is correct. This is bush. Bush. So
No,
we can.
no. In the given data,
This is bush.
no, in the given data only, I mean, only
So
one bush is there.
let's,
Right?
let's plot a classification matrix and see the result.
Okay.
Clear, right?
Yeah.
Why do you worry much? See, this is precision. Okay, and more so, if you want to predict confusion matrix, we can predict confusion matrix. The algorithm accuracy is around 85%. Okay, but of course, what our we will be able to understand everything. It is using C1. No. See this now. So you will see this. Where is this is misclassification, right?
Yeah.
No, this is correct.
No, this is correct.
Correct. Where is more of misclassification happening?
Is there no? That
Lot of-
Donald Trump
George W. Bush is highly misclassified, right? Useless fellow, yeah. Understood. So, Anjali, you are doing this exercise. You will correcting all your photo, your family's photo, and try to do this drill.
I'm trying to connect Trump.
Huh? You're connecting, correct?
Trump.
No, she targeted Trump only. She's
Trump,
applying
big
visa.
Trump fan.
Yeah.
No, yeah. He has given one quote. What affects the anything is always
Okay. So I'll just sum it up. Some properties of SVM. So we have seen SVM for classification. You can see SVM for regression also. Okay. I'll show some examples of it. Should give some function names. Okay. So for regression, what is the function you'll use? SVR. Got it, right? SVR. Okay, you same by regression, it will whatever values that all it will do it will not apply any it will predict the line. Whatever it's similar to your linear regression in one way. What it will try to predict the line, which is best representing the data set. Then you can use the data set. Then okay, so the SVR, I'll just mention it here. We can just refer to SVR for. And if you remember this, just keep a note of this diagram. Where is my diagram? Okay. In this case, regression, you'll see SVR. Okay. So here, less than 10,000 data. Yes. Few features should be important. Feature selection. I mean, if it is no, all the features are important, then you'll use SVR, kernel linear. Understood, right? Like this is less than 10,000, right? Less than 100K data. You go here.
Less than greater than.
Data.
Hey, this is greater than 100K.
Less than.
Less than 100K, you do this process. Okay, if it is greater than 100K, then if the data is lot, then you do SGD regressor. Understood, right? Start integrating this regressor. You don't see regularization and all those techniques you don't need when the data is too large. Remember this thing. So all the tricks are required when data is less. If data is large and if your large computation power is simple, algorithm will also give you good results. Got it, right? Because data will be automatically generalizing itself. Okay, so if you have large data, you don't need even random forest. Decision tree will be good. It will generalize. Understood, right?
So then it's reverse.
Huh?
When we see the data more, then we see that more complexity.
If data more, then the problem is actually in the
Easy.
understood, right? The data will automatically generalize itself. The important interview question. Okay, if the data is more, what do you do? If the data is 10 lakh data, I mean 1 billion rows every day you are getting, what do you do? Normal function will give you good result. Okay, generalize that. No need for random boosting and all that. Understood, right? So I'll just mention a few things here. Read about SVR. Okay, and this is for random regression. Then okay, so you have SVR, linear SVR, NU SVR, whatever you have seen for regression, you have it for regression also. All these options are there. Okay, so then you, what is the third thing that I discussed here? It is used. What is the third thing? It is used for anomaly detection also. Let me show something in that. Okay, so as I spoke earlier, how do you do that? You basically try to uh, you basically try to see how well your data can be fit in. If there is too much of data, I mean, if there's some data is outside your generalized logic, you see there is outlier. And that is basically how it works. So, for example, you are predicting in your normal data, you have to use linear regression to find outliers. You'll see whatever line you are predicting, some data is very far from it. We'll call them outliers. Okay, that is for this also. It will create a predictor. So based on some data, and if some data, if for some data the cost function is very high, then you'll see those are outliers.
The outliers, what will
See, outliers is very useful in customer analysis, right? You want to find who are the outliers in the data. First, you always remove those outliers from the data, then you run the algorithm. Okay, otherwise your algorithm, like if you want to find purchasing power, you'll remove money from the data set, isn't it? Huh?
Can we use this way also like this?
Huh?
Why money we should do?
Because he will skew the data. Right. I mean, no. This is how you should do. I mean, if you want to find purchasing power of a particular mall, you try to first remove the people who purchase a lot, who don't purchase at all, because they are skewing the entire information. You always do on the 80% of the data.
Can we use outliners in this way? Like outliners are actually outside.
Outside the prediction radar, you can say.
So we can use that data also to predict it.
Right.
So that we can bring them in line.
No, you don't bring them in line. You just get rid of them.
Okay.
Okay, because you want to predict a generalized algorithm, not a specific one. Okay, so that is why how you use outliers.
Maybe some analysis why this person is not investing in something. Outliners.
That is very good. I mean, of course, investigation on outliers you can definitely do there. Okay, investigation, but that is why fraud detection. Those outliers, frauds are nothing but outliers actually. Okay, so yeah, we are done with that. Okay, go through the practice problems. Now the time you should be investing a lot on working part of it. Okay, how to deal with various problems. get started with solving problems actually. Okay, and don't delay too much. After this, if you don't do this for 1 week, all will be starting to evaporate out. Right, one?
Yeah. Almost not.
Okay, so do that. Okay, I'll inform in the other batches as when we are doing the projects part, right? Again, just for revision, I'll tell you guys so that if you want to attend those. And the others also, I think few folks missed out the last few classes. Okay.
By today it's over.
Yeah, today.
There are a few more pending ones there, no?
Which one?
Time series is not done.
Oh, you guys, we have to do matplotlib, right?
Matplotlib is
Oh,
missing.
you guys missed out, right?
And unstructured data.
That part, right?
Yeah.
Yeah. Oh, we didn't do that classes. We didn't watch those classes. Hey, we did with you. We didn't do with them, I guess.
No.
Huh?
No.
For us, basically.
Oh, actually, for you guys, we didn't do that. Well, then we could take one more class then for you guys separately. Okay. Actually, today I have to leave. I have to pick my parents from airport. Okay, so that's the reason I'm wrapping up now. Okay. That's it.
So next week we'll cover.
Next week, I think 1 hour or so it will take 1 hour.
And then for the AI, it will continue.
Yeah, it will continue. I think next week itself. There are 2 people.
No, still something is important which we missed it. Chi-square is pending in feature sections. No, only we have done random forest and decision tree.
Boosting techniques, add a boost, all.
And Gini entropy.
So I'll tell you. So that is decision trees part. When you did decision tree, we plotted the tree, right? There, that's that component. So let me use. So I actually done a lot of extra.
Few things I have noted down here. Anyway, today your hurry.
That's okay. Let me just show it and tell what exactly is done.
Yeah. Anyway, next week we will come now.
And cover up all the other. Try to revise all the things. Let me know if you have any doubts.
Yeah.
Okay. So next week we'll do more on whatever nitty-gritty thing is pending, and more on doubt clearance part of it. Okay. So we did a few things like nearest neighbors and all. I was not mentioned here. Okay, that we did last time.
No, it's
Nearest neighbor is there.
and somewhere it's.
Actually, when you started the course, this topic was not there. Recommendation engine. So I just added it and changed it. Right. Then you have stake regression boosting techniques we did here.
2 times that K means class. And one it is K and it's changed.
Then we did this boosting techniques. Right. Then K means web scraping recommendation. So what are the things you mentioned? Naybase, right? Yeah. I'll just show where it is.
LDA is not done. LDA. PCA is done only. But
LDA is not there.
It's not there. Okay. But
see, just go through another notebook.
Okay.
I think so. This notebook, right? Here there is a topic on. See, I mean, I keep changing the content because it has to be that way. Here, you do this. Refer to this.
Anyway, by this beginners one, I'll go through this one.
So whatever is best, right? It's very simple actually. The feature selection part. Just go through this. Yesterday I was doing this chi-square and all that, right? That is nothing but a parameter in feature selection. Yesterday we were doing these 2 things, right? One is chi-square and F regression. Go to the bottom of the page. Yesterday class you missed. Okay, go here. In the bottom of this page, right? You'll see this regression and chi-square is there.
No. This that middle one is there, no? In the classification.
Chi-square.
This is missed. That the mutual info class that also missed. Only F class we have.
So then this I can do in 2 minutes. Just wait for 2 minutes. So in select K first function is there, right? It will find you important features. Okay, among
like K best.
K best exactly. This is the function. Select K first.
Then what's the
Selective
main
best,
base?
not sorry. It is not first. Selective best. See this guy, right?
Could you share yesterday?
Yeah. So here, if you see here,
Anyway, I'll do one thing.
no,
I'll go. No. Let me.
Acha, acha.
I'll go through all the what you have uploaded.
Right.
I'll note
Sure.
something.
Okay, so
I'll
tomorrow
come.
if you collect whatever topics
Oh.
you to revisit. I think we'll need one more. That is okay.
That's what
So,
we'll
so
go.
just collect whatever you need to revisit. We'll do it.
Could you share yesterday?
Recording, yes, I have. Stop now. We'll get going.